Hey everyone, Professor Sura here, and welcome to Chapter 10, Organohalides, also called alkyl halides for the most part. Organohalides is a more encompassing term, but you'll hear me call them alkyl halides more often. So don't get confused by the two. So here's the structure for the lecture. As always, we're going to practice naming and drawing of these. And then we'll learn how to prepare them, what they can do, some unique properties, and then how we can use them in reactions to prepare either new functional groups or go back to some old functional groups and just add these into your repertoire. One of the coolest reagents that we learn about are called the Grignard reagents, one of my favorites. So I'll make sure to talk a lot about that. We'll keep talking about alcohols, even though the alcohol chapter isn't until later in the book. And then we will introduce something pretty new to you all, these organometallic coupling reactions that involve the Grignards, but there's some other very interesting types of reactions that occur. So I'm excited to share with you the new stuff in this reaction on this chapter. Okay, so these are all various organohalides, and this is just showing you where they are commonly used. So trichloroethylene is a solvent. This is used as an anesthetic, this halothane. Tetrafluoropropene is a refrigerant, and a fumigant is bromomethane. So some of these you can name, some of them, well, we'll practice the naming, but there's the systematic way of naming stuff. So here are those examples. It's going to be just like we were naming our alkanes before, and our alkenes are going to follow the trend. Name your longest chain and make sure you name it so you have the lowest number on the substituents as possible. So in this case, we have numbering from the one on the left versus numbering from the right. We end up with the more accurate naming. So I'll let you practice those. But this shouldn't be anything new. You've done this a few times. We're just kind of refreshing this. You learned a lot of this back in the alkane chapter as well. Remember, you want to prioritize the alphabet when you have the option. So you're going to the first one, so this one is the only way to number it. That's how you're going to number it. So you have the lowest numbers on the substituents, and then when you actually put that together, have the letter B comes before C, before M, etc. So don't worry about it's not that this is coincidental that it's 1, 3, 4. You want do it by the alphabet, regardless of the numbering. When the numbering is good from either way, so you could have numbered this 1, 2, 3, 4, 5, 6, and that still gives you a 2, 5 substituent. You're in charge of the numbering. The molecule doesn't know you're numbering it, right? You put the number on the lower substituent alphabetically. So you choose to put it on the bromo specifically because bromo comes before methyl. And then there's some kind of common names. So iodomethane or methyl iodide, and then 2-chloropropane or isopropyl chloride. So remember your isopropyl groups when you have your 3 carbons and you're substituted on the middle there, like isopropyl alcohol or isopropyl chloride or just an isopropyl substituent. And then if you have any alkyl halide or a halide on your ring, you're just going to name it as that compound. So either bromocyclohexane or cyclohexyl bromide. This is usually what I call it for the common names. They're both perfectly fine. And remember, as long as you're naming it something that's in one of the systems and it's unequivocally, unambiguously that compound, you're in good shape. So the cool thing about these alkyl halides is that they create this dipole, right? So we end up with an electrophilic carbon. So X in this textbook, unless otherwise noted, is any halogen. So chlorine, fluorine, bromine, iodine. And we end up with that partial positive on the carbon, which is the cool part. That's why these are such an interesting functional group, because we have an electrophilic carbon that's capable of performing those types of reactions and acting like an electrophile. Okay, we've reviewed how to prepare alkyl halides before, back in, I think, chapter 6, doing these radical chain reactions or radical propagations. So if you have light, that's what the Planck's constant and frequency there represents light or UV light, and you hit that with your halogen gas, you're going to have those radicals formed, and they keep going. You'll replace one hydrogen with a chlorine, so remove one of those, and then it goes again and again and again. So this is definitely going to give you substituted alkyl halides. It's really hard to stop it at any of these points. mostly you're going to get this carbon tetrachloride, which is great if that's what you want, but it's definitely not your go-to method for for halogenation. Here is a review of those steps. The initiation step is the generation of that radical. And then once that radical is formed, it can do a bunch of damage, is how I always picture it. But it can react with pretty much anything. So you can just abstract another hydrogen, or you can react with another chlorine and reform the chlorine gas. So it's kind of a mess in the propagation step. But you eventually will have it where you end up with the methyl radical and your chloride radical, one of them, forming what you want, maybe what you don't want, but are also forming the reactants again, right? So eventually you end up with the more stable products. But so again, not the best one to control, but this definitely occurs. Some other examples. So the previous slide did methane, which is just one carbon. When you have multiple sites for radical substitution, you can get a mixture of things. So here you'll see a 30-70, where we get 30% on the primary carbon and 70% on the secondary carbon, right? I'm going to be talking about primary, secondary, tertiary carbons for a while, and some other new types of carbons. So it's really good to review those very general terminologies: primary, secondary, tertiary, quaternary carbons, allylic, phenylic, benzylic. So we'll talk about this some more. When you have a more branched alkane, you can get a variety of products again. And in this case, we're seeing more substitution on the primary carbon and a little bit less on the tertiary. So we can start to predict some trends from this. Right, so through lots of reactions and studies, they found that the reactivity of these primary, secondary, tertiary carbons increases like this. So this is going to be more reactive, and this is for the chlorination reaction. So specifically the one we were looking at back here, but we can extrapolate it to make some more assumptions. So we find the tertiary is more reactive than the secondary and the primary, and it has to do with the stability of that radical. So just like when we were driving our carbocation reactions, the stability of the carbocation was what dictated the final product, and it's the same thing here. It's just the stability of that radical, and it's stable for all the same reasons: the inductive effect, more substituents, hyperconjugation, all those things. So I want to review, and we'll talk more about that. But this is also a review of another halogenation reaction you've seen before. You can get a dihalide by using either bromine gas or chlorine gas, or just a monohalide by using HBr or HCl or HI. All right, so the new reaction that I don't think you've seen yet is called this allylic bromination reaction. So the allylic positions are the ones next to the alkene. If your alkene's right here, it's 1 over. So sometimes you have 2 allylic positions, sometimes you only have 1. I guess sometimes you have none also. You have to have adjacent carbons. So like ethene wouldn't have an allylic position, but propene would. And then these conditions, in my mind, when I study this, I just picture them as a bromine radical, because that's kind of how it behaves. This is called N-bromosuccinimide, or people will just call it NBS for short. Again, in the presence of light, and then carbon tetrachloride is just a solvent to make the reaction work. But what's happening is you're taking one of these hydrogens in the allylic position, abstracting that with the radicals, and then replacing it, substituting it with a bromine. So again, with an allylic bromide, you can practice your alkene naming here. And pretty good yield, 85% is pretty good yield for a reaction. And again, this is what they get experimentally. It's what we actually obtain. Okay, and this is just a reminder. When you see these conditions, you want to picture bromine radical. It's a little bit more complicated than that, but that's going to put you on the right track. So here's a little bit more complicated. So this is not quite an arrow pushing mechanism, even though there's arrows. So you can definitely read through this and make sure it makes sense. Read through it once, read through it twice, take a break, read through it for a third time. But essentially what happens is this bromide radical is formed, and then that radical abstracts. So single-headed arrow. That's hard to do on my computer. Single-headed arrow down to that carbon. So now we have our radical on this position. You could have done the same thing down here because it's symmetric, so don't worry too much. We're just showing one hydrogen. Once you form this new alkyl radical, this vinylic radical, that's going to react with the Br2 Again, they're not showing the mechanism. All these arrows are just pointing out where these things are coming from. This is showing you the bromide radical being generated in step 3. This is showing you the HBr being used in step 2 to react and form Br2 to form, that's like in situ or in solution formation of Br2 gas. I'll repeat that. In situ is a chemistry term. It means like in the flask or in the vial. You might have heard of in vivo if you've taken biology classes. This means like in real life, so like in animals or in cells. And then in situ is like in your flask. So I just casually dropped it in there, but I want to pause and make sure you understood what I said, because I was definitely speaking Latin, which doesn't happen often. So we're generating Br2 in the reaction, which comes back into play in step 3. And that's really what's happening here. Br, and then this radical is going to pick up one of those Brs and then break this. Again, trying my best to draw the single-headed arrows for that homolytic cleavage. Again, a review back from your alkane chapter or alkene chapter. Homolytic versus heterolytic, which is where we are moving the 2 electrons around. So just keep all your terminology down. I know it's a lot. And then this is the step that actually forms your vanillic halide. So there's a lot to take in there, but it's a pretty cool reaction. So the allylic position reacts because it's weaker. The bond is weaker is one way of thinking about it. Your alkyl position, it's really hard to break those carbon-hydrogen bonds. And then the vanillic position is pretty strong as well. So this is the weakest bond, which is why it's the easiest one to break. So that's also explained through stability. And this is just adding to, you already kind of have this down. That's your review. Remember, methyl is just literally a methyl group. Primary is like your primary on the end of a chain, somewhere in the middle, highly substituted. And then when you have the allylic position, you're way more stabilized. In the vanillic position, you're way less stabilized even than a methyl group. It's just this is extremely exposed and can't do anything to stabilize itself. So it's very, very reactive and highly unstable. The allylic, on the other hand, super stable. And you can ask yourself why. I think I have the next slide. If you said resonance, because that's generally the answer to most stability questions, then you were right. So you can move that radical around. They do a pretty good job of drawing the arrows here. But there's your resonance arrow showing you that both of these exist at the same time. Here are some diagrams, some orbital diagrams showing the electron kind of moving around the top. Here is another like a top-down look showing the lack of electron density at each of the allylic positions. Right, they're not showing you the double bond because it's kind of implied with this picture. I think that's all I give you for pictures. So the whole idea is that we generate this allylic radical and it's stable. So it lasts longer, so we get reactions there. Okay, so here is your terminal alkene, right? We have the alkene out here, and so there's only one allylic position, and that's going to be right here. It's your alkene, 1, 2, and then the allylic position is the carbon next to your alkene carbons. So it's going to be on carbon 3 in this case. So we hit it with our halogenation or radical conditions and generate the radical at this position. So this can undergo resonance. So we have it alternating between carbons 1 and 3. 1, 2, 3. And the more favored one is actually the reaction at the primary, or this is allylic, but it's on the more exposed carbon. If you think about this radical here is in the center of that chain, not center, but it's kind of like hard to get in there, versus this radical, which is on the end and easily accessible. So that's a steric hindrance argument. It's easier for the bromine that wants to come in, my radical, and quench. It's easier for it to get to the end than to try and fit in between all those carbons. So you get a really low yield of the reaction on the left and a pretty good yield of the reaction on the right. And yeah, you get a mixture of transistors. It's not, I wouldn't call that good stereo control, but you still end up with this product, and depending on what you want to do with it, you might not care about the cis-trans ratio. It's about 50-50 there too, right? It's not any control of the stereochemistry. All right, so the cool thing about these vanillic halides, right? So this is the review for what we just learned how to do. And this book loves to throw like a new reaction in you and then just turn into something else immediately. So in the presence of KOH, your potassium hydroxide, a very strong base, excuse me, you can remove that bromine and generate this diene. And I think the mechanism shows up in later chapters. But and then we don't use the dienes right away, but these are super important intermediates as well. So keep that in your mind for when we need to make dienes in a few chapters. So new stuff from this, and then also new, but like the stuff we just spent 20 minutes talking about was that one, and there's a new, so you get like 2 new reactions right here. All right, we can also make these alkyl halides from alcohols. So remember, we learned how to make alcohols from alkenes. A couple different ways to do that. Add that to your arsenal. So you can go from alkenes to alcohols, and once you have the alcohol, you can substitute them using, in this case, just like HBr, HCl, so hydrobromic acid or hydrogen bromide gas, etc. We get our dehydration product, the H and the OH form water, and we end up with a new carbon-halogen bond. And the same reactivity trend holds. So your methyl alcohol is going to react less than, start from the top. Tertiary alcohol will react the most or the easiest, secondary, primary. So still a good trend to keep down. Generally, if you have this trend down, the other functional groups fall into line on the other side, and sometimes it flips. So just keep the trend, and you should be good. Here's that reaction specifically with hydrogen chloride gas. Again, not to be confused with HCl aqueous hydrochloric acid. So this is gaseous HCl. It's all covalent. There's no acid-base chemistry technically going on here. Okay, and we're just going to, again, swap out the OH, add the chlorine. Ether's your solvent. They do it at pretty cold temperature. That's just ice. An ice water bath will do that. We've done reactions in ice in the lab, I believe, or at least you've cooled stuff down to ice temperature. So more interesting ways to convert alcohols into alkyl halides. So this is called thionyl chloride. That's the SOCl2. Looks something like this. And pyridine is just your solvent. So look for the green. They have it in green as the important part. And it's the same idea. You're swapping out the OH for the chlorine. This is cool because it doesn't react with any of the other functional groups. Notice the ketone here is just chilling, not doing anything. You can have some big bulky benzenes in the way, right? So it's a really good way to get in there and turn any alcohol into a, in this case specifically, is going to be chlorine, right? The SOCl2, your chlorine's coming from the thionyl chloride. Works really well for secondary alcohols, right, on secondary carbons. And then this PBr3, or phosphorus tribromide, I still call it PBr3. Ether's your solvent. This is like a little warmer than room temp. It's actually probably the temperature of our lab sometimes, right? It's a little warm in there. But a great way, again, just to substitute your alcohol for a bromide. Excellent yields. Like, these are really great, honestly. Another way to make a halogen, we don't talk about fluorines a lot, but you could make an alkyl fluoride. Let's call this fluorocyclohexane by hitting it with HF and pyridine, right? So you can make the big three so far. We don't do a lot with iodine just yet, but you can start making all of these halogens using just, all of these are really just any alcohol, ROH, plus your hydrohalide, and you're making that new RX bond and water. So it's a nice condensation reaction. Okay. All right, Grignard reagents. These are one of my favorites because you can take like anything and turn it into a Grignard. So, and then the Grignard can do anything you want. It's really, really good stuff. So consider a primary, secondary, tertiary, alkenyl, aryl, halide. So this is a super general formula. So you can take an RX, where R is any of these and any of these in pretty much any combination. You hit it with magnesium metal, so it's like metal filings or shavings in ether or THF, And this is what is called a Grignard reagent. I can't stress enough how important this is as a reagent. You can just buy a bottle of this from the chemical supplier. And that's what I did a lot of research with. You order some Grignard reagents if you don't want to prepare your own, because they make them in various concentrations and various solvents and all of that. All right, so why do you care so much? So these alkyl halides we've been spending all day talking about have that partial positive carbon because of the partial negative iodine, right? Why does that exist? That's a dipole that exists due to the electronegativity difference in the carbon and iodine, right? I just said we didn't talk about iodine. Here he is showing up. You make the iodine the same way you would with some of the other reactions, so we can talk about that more if you want. You hit it with that magnesium metal and ether, and the magnesium inserts itself basically into this bond. So now you have a carbon magnesium iodine bond. And remember, magnesium's a metal and generally behaves like a 2+. So they're showing this partial negative on the carbon. It's wicked negative. It's almost a formal negative. You can even see the blue here, that very lack of electron density. It's all out here on the iodine. Iodine's nice and electronegative and all that, and the magnesium is kind of like this little bridge. So we've essentially created, and in my mind, I picture it just as a negatively charged carbon. It's super, super negative, not officially formally negative, I guess, according to this picture. But for all intents and purposes, you can treat that as this carbanion-like thing. Okay, so here is a specific example of what you can do with the Grignard. I think I have some more exciting stuff showing up. We got to learn some other function groups. But for now, you take any alkyl halide, hit it with the metal and ether, and you form your Grignard reagent. Please know how to do this. This is a great reaction. And this is called quenching. Quench it with water. We'll see how this is a CH2. It's just that. I don't know if I have the mechanism on the next slide. Picture this negatively charged carbon picking up a hydrogen and popping that over to make OH minus. And now we have a CH3. So you can go back and turn your alkyl halides, right here, alkyl halides, into alkanes, or at the very least, just remove your halide, which you might want. Maybe you end up with some stuff there you don't want at the end of the day. So just keep track of your general reactions. There are way cooler things that Grignards can do. We just have to introduce them when we learn some other functional groups. I'm surprised we don't have it on this slide, though. I'll see if they show up in the homework. So other organometallic coupling reactions. These are butyllithium, lithium reagents. Butyllithium is one of the more common ones. It behaves similar to a Grignard. Basically, you're using lithium metal instead and a slightly different solvent, but you're completely removing the halide and putting lithium in its place. So in this case, you have 4 carbons and that lithium ion on the end, and you just have I can picture as a negatively charged carbon, and you can see that. Oh, I think that's a picture, I guess, but right there is your negatively charged carbon. And you're going to treat it just like a Grignard, essentially. These are organometallic reagents. I guess I didn't hammer that name enough. Organometallic, meaning you have an organic portion and a metallic portion. So there's a whole field of chemistry is organometallic reactions and reagents. And I want to point out, this stuff is highly, highly reactive with oxygen and water. It's called pyrophoric, which means pyrophoric. It basically catches on fire when it hits air. So you're going to use special conditions to work with this, and we can talk about that more in the lab. But these things will explode and cause lots of damage if not handled properly. So one thing to read them on paper, another thing to practice them in the lab. So just be aware of your chemicals and what you're working with. Okay, another type of organometallic coupling reaction are these Gilman reagents. And again, at the end of the day, they're all doing the same thing. It's just some things are more susceptible to reactions working like in real life. So we're showing you a couple different ways for things to work so that when you're actually in the lab testing things, you can try a couple different routes. So the Gilman reagents are prepared from your organolithium reagents. You need 2 equivalents of them and this copper iodide, right? The copper is copper 1 iodide right now, but there's some other coupling that occurs. And then you have your ether solvent. And this is your Gilman reagent. Notice that you have 2 equivalents of your halide on there. A copper negative, which is really weird, and then lithium plus. This is your Gilman reagent. Probably that's how I would normally write it. The reaction you care about, so first know how to prepare the Gilman reagents. Just copper iodide and any of your methyl lithiums or alkyl lithiums. In this case, we're doing methyl specifically. And once you have that Grignard sorry, I'm all about the greens. Once you have the alkyl halide, you can take one of those equivalents and replace it and kick off that iodine. So notice we made a new carbon-carbon bond, carbon-carbon bond right here. And this is all the byproducts. You can look at the mechanism and figure those out if you want, but I mostly focus on the major organic product, the reason we're doing the reaction, right? Ether at 0 degrees. I have a couple other examples here. Right, so these are really cool. So here is your Gilman reagent. This is the CuCl, the copper lithium side of it, 2 equivalents. All you're adding is this portion. And N stands for normal, so this is normal butane, which means a straight chain, opposed to like isopropyl or sec-butyl or tert-butyl. It's just N-butyl copper lithium. Just find your alkyl halide, in this case this is a vanillic halide, and replace that with your Gilman reagent's alkyl portion. This is the new bond we're making. And they're just not drawing out all the carbons. So C4 is just a 4-carbon chain. So we are doing a chain lengthening reaction, which is super cool. We can start building chains off of these alkenes. Notice the alkene's not reacting, so we can further react it later after we build the chain to what we want. Here's iodobenzene reacting, and you can substitute a benzene ring this way, which is super cool. Again, you're adding just one of those methyl equivalents, making a new carbon-carbon bond. So I know I'm hitting you with a lot. This is a heavy chapter. It gets a little more heavy with these Suzuki-Miura coupling reactions. This actually won the Nobel Prize back in, I think it was 2008. This is super powerful. So it's used to make these bi-aryl compounds, bi meaning 2, aryl meaning these aromatic rings. More often than not, they're benzene. But if you look at major pharmaceuticals today, and even a lot of the major active reagents in a lot of natural products and oils and things like that, the benzene ring shows up a lot. So being able to couple these rings together, and like this is like the bi-aryl group. It's just these 2 benzene rings coupled together. Being able to do this is super powerful, and they're able to do this in pretty mild conditions. The palladium catalysts are, I guess, relatively inexpensive. They're still expensive, but this is a very powerful coupling reaction where you're taking this boronic acid derivative, this BOH, there's 2 OHs, but it's like you can picture like a carboxylic acid, but it's a boronic acid. And any alkyl halide, I'm pretty sure the iodines work really well. And you're coupling, so this carbon and this carbon are being popped together. You're making this bond, and they don't even show you the byproduct, right? They don't care either. Get rid of this stuff and pop your rings together, and everything else comes along for the ride. The methyl groups are just chilling. So palladium triphenyl phosphide is, or tetraphenylphosphine. The pH here is a benzene ring. So these are benzene rings. So this is a big bulky palladium. Calcium carbonate and THF THF's your solvent, and calcium carbonate is a base needed to propagate the reaction. The mechanism is a bit complicated. We'll go into more detail later. I think I have a summary slide of it on the next slide. But these are like this is your go-to organometallic coupling reaction. If someone says, "What's your favorite besides Grignard?" You're gonna do the Suzuki-Miura coupling. Right here's just a more specific example. This is paramethylbenzene boronic acid. Don't worry about naming that yet. All you're looking for when you're working with these, look for that boron with the 2 hydroxy groups on it, and then find your alkyl halide. I'm not going to give you anything weird where it's like reacting with this. Like this is just a nitrile on the side, or a cyanide substituent, right? Wherever that boron is attached, and whatever that alkyl halide is attached, that's where you're going to make your new bond, right? And that's what goes on here. So this is one step, and here's your reagent. Look for you need the palladium catalyst. That's really the star of the show. Here's potassium carbonate. That's just another base. Here they use calcium carbonate. You need some type of carbonate or a weak base, a weak inorganic base. So these 2 arrows just mean many steps later, but this is one step in the coupling to form valsartan, which you can see the bi-aryl group right here. They turn that nitrile into a pyrrole ring. They fully functionalize that methyl group with some other reactions we haven't learned yet, but it's multi-steps. but valsartan, I believe, is like a heart pressure or what is it? Yeah, like blood pressure or heart disease medicine. Um, so big money in these reactions is why it won the Nobel Prize too, right? They were able to do these couplings super easy. So this is called a cyclic mechanism. It's a reaction mechanism. You haven't seen it drawn like this before, so feel free to pause the video and kind of read through it and try and get your grasp on it. But what happens is those aryl halides, right? So that's one of the reactions you need for your coupling. This is the same Suzuki reaction. And here is your aromatic boronic acid. So in this case, AR just stands for aromatic. And here they put a little prime on there to differentiate between, you can have one aromatic and another one. And at the end of the day, those two things react to form your bi-aryl product. All right, so that's what we've been talking about. The way this works is you end up with, they have palladium, so you kind of start right here. This is your palladium metal, PD is palladium. L is just a ligand or a ligand, or you might have also heard it called a chelate. Those are all the same thing. And then N down here is any number of them, because sometimes you have a couple on the side, sometimes you have a couple more. It's a little weird. But the idea is that the palladium with its ligands inserts between the aryl halogen bond. So notice right here, it just kind of hopped in the middle. So now I have an aryl palladium halogen bond. Then you end up with this metal transition where the halogen switches with the new aryl group. And now I have my aryl palladium aryl compound. And the halogen went off to that boronic acid. This is where the base comes into play. So your carbonate, whatever is attached to, will come in and pick this up and quench that. So it's not going to make any weird byproducts. And then this palladium is eliminated and goes back to here. And you make your new aryl-aryl bond. And then the palladium continues in the catalytic cycle and does it all again. So you don't need a lot of palladium. You need a couple little specks of that. So practice this. It's very cool, and we talk more about it later on in the semester. I don't think this was in the textbook when I was a student. That's how recent this has been discovered. So it's still pretty cool. Okay, so we're going to do a little bit more review here. We've talked about a lot of reactions and hinted at if they're oxidation or reduction. Remember, in general, if you're making more bonds to oxygen, more carbon-oxygen bonds, you're being oxidized. And if you're making more bonds to hydrogen, you're being reduced. But there are some other cases where you're not necessarily doing that, or other ways to categorize it. So this is like the review. Here we have a carbon-hydrogen bond. We get rid of that and make a carbon-chlorine bond. So therefore, it's oxidation because we're making less bonds to hydrogen. If we take that carbon-chlorine bond and then react it and turn it into an alkane, this is a review from this chapter. This is also a review from, I guess, this chapter and the other chapter, chapter 6. Right, this is your Grignard conditions, right? I'm never going to say, hey, it's a Grignard, but if you see magnesium metal, pop it into your alkyl halide. Again, getting distracted by the Grignards. But this is a reduction because we're adding a carbon-hydrogen bond. So these ones you should recognize. If you're making carbon-hydrogen bonds or breaking them, you should be able to figure out if it's reduction or oxidation. Okay, it gets a bit more complicated when we're not adding hydrogens or oxygens, right? So in this case, we have carbon-hydrogen bonds, and then we make our vicinal dihalide, and we make new carbon-bromine bonds. So this is still considered an oxidation because we're making bonds to a more electronegative element. So it's kind of like when you learn about acid-base chemistry and it all makes sense, and they threw Lewis acids at you, and they have nothing to do with hydrogen. It's all about electrons. So in this case, we're defining oxidation a little bit differently by making new carbon-something bonds that go to more electronegative elements. And if you do both at the same time, which this doesn't, I never talk about it quite like this, but you call it neither oxidation nor reduction. Because you're adding a hydrogen, which is reduction, and you're adding a bromine, which we just learned is oxidation. So they kind of cancel out. So just get your terminology down and to talk about things like oxidative insertion or oxidative elimination. We want to be thinking about what that actually means. And here's just some examples, like, so your very boring unoxidized alkane, fully saturated, so it's ethane. And then as we make more bonds to carbons or more bonds to oxygens or chlorines or nitrogens, it's getting more oxidized. and we make multiple bonds to carbons, or like a double bond to oxygen, a couple more chlorines on there, make this imine bond, which you're not quite familiar with yet, but it's called imine. We're getting more oxidized, and then sure, carboxylic acid, multiple halogen substitutions, a triple bond to nitrogen, where it's making more and more bonds, so it's getting more and more oxidized. And then these are, some of the heights of it all. It's got 4 bonds to oxygen, right? So it's a lot going on there. So just keep track of what something being highly oxidized versus, highly reduced at this end means. And that's it for the chapter. That was a lot. Like I said, I would say, please don't forget how to name these. Students kind of forget that, and they freak out with all the reactions, which I understand. Review your radical halogenations. Some of the mechanisms we talked about we'll review, and we introduced some new concepts. The allylic bromination is the first new way. In this chapter, we figure out how to halogenate something, and then we also added the thionyl chloride and the PGR3. We talk about resonance because it wouldn't be organic chemistry without drawing some resonance structures. We turn the alcohols into alkohalides. That's where your PBr3 and your thionyl chloride come in. I was getting ahead of myself. Greener reagents we do a lot more with, so we're going to come back, as well as those other organometallic reagents. I think I hyped them up a lot, and you didn't get to see everything they did, but they will come back, I promise, and then we'll do some more stuff with them. And then just a review of oxidation reductions. And then it says coupling reactions, but like the Suzuki coupling reaction is super powerful. And there's a big variety of coupling reactions. The Negishi coupling, we did Mayura, Suzuki, what else? Heck coupling. There's a whole bunch of coupling reactions that we'll talk about later. So I hope you enjoyed the chapter. Please let me know if you have any questions, and I appreciate your time. Enjoy the rest of your day.